Hello Math 126 fans, I'm going to make a short video on surfaces. This section, I think people overcomplicate, students, instructors, TAs, and there seems to be people hate it because of the formulas, but it's really cool. There's some cool shapes we get to learn, and we need them in the sections to follow, and it's actually a really easy section, so I want to dispel a few things. Basically, it boils down to this. We have cylinders. And those are things where one variable is missing. So there's only two variables. And in those situations, you just draw whatever the 2D graph is, and you extend it in the other direction. That's it. And then we have what we call paraboloids. And that's you have all three variables, and two of them are squared. And I'll talk about how you can remember that. And there's two flavors of those. And then I'll explain where those names come from. And then we have hyperboloids. I know the names are sort of weird, but the pictures are cool, and I'll show you some of them. And we have three flavors of hyperboloids. And then we have one other one, which I'll list here, but it's basically a sphere or an ellipse. Ellipsoid / sphere. And it's easy to remember those. I can tell you where the names come from. So here are some examples over here. We basically look at traces. So right away you can say this is a cylinder. It's that easy. This is from my lecture notes. I have students just name them off, and by the end of class we can all just shout them off and go home and do the homework in almost no time. There's a couple problems in there, of course, that take longer. But here, what do? You do traces. So what we do is we look at it from a few different sides, meaning if x was replaced by a number, it's a hyperbola. How do we know it's a hyperbola? Because both are squared and there's a minus. You have to know a few shapes. You basically need to know if there's a plus between them, maybe a number, that's an ellipse. If there's a minus in there, that's a hyperbola. And if only one of them is squared, it's a parabola. So if you know the 2D shape names, then the 3D shape names are quick. So you cover up this x and you say, okay, that's hyperbola. That's just if you cover up the x. And then you play the same game. What if you replace y with a constant? Ah, that's a parabola. What if you replace z with a constant? That's a parabola. Now, there's always a few subtleties if we want to dig deeper, but I always wait till chapter 14 because we're going to do that. If two of the traces are parabolas, we're going to call it a paraboloid. And in this one, we're going to call a hyperbolic paraboloid. That's where the names come from. I don't ever memorize the names. I just look at the traces. This means the trace in two different directions is parabolas. This means the trace in two different directions is a hyperbola. That's all it means. So I think people overcomplicate this dramatically. And then it's just a question of what the adjective is. Now, the only part that does have a little more to it is here, that hyperbolas come in three flavors. There's one sheet, there's two sheets, and there's a thing called a cone, which we usually don't call a hyperbola, but it's a cone. So one sheet means it does have, it's all connected. It has a smallest radius. A cone means the smallest radius is 0. It's very skinny. And two sheets means it breaks apart into two. But that just depends on the constant on the other side. So in order to have this, you have to have all three squared. All squared. Here you have 2 squared, which makes sense because that's what you'd get. And there's a minus between them. So these are the ones that are hyperboloids. That's a hyperboloid. That's a hyperboloid. That's a hyperboloid. By that I mean it could be one of those three things. If you did traces, you would see this. But the interesting thing is the trace when it's a circle. And what I mean is if I did the traces, if I covered up the y, it's hyperbola. If I covered up the z, it's hyperbola because it has 2 squared. There's a minus between them. So this is hyperbola. Hyperbola. But there's one trace. If you cover up, you get a circle. But in this case, it's sort of weird because if you replace z with 0, you get this, and that doesn't make sense because you can't have a negative. And that's when you get two sheets. So if the third trace doesn't make sense when this is a 0, it's a hyperboloid of two sheets because there is nothing there. The alternative way to do this is to multiply everything by -1 so that you only have one minus. And if you multiply so that there's only one minus and the other side is a negative, then it's two sheets. Here we have, when we do the traces and we replace x with 0, we get a really skinny ellipse. That's a cone. So this is a cone. This is two sheets. And this, if you move the 6 to the other side, it's a positive. That's one sheet. Those are the names. So just a quick few visuals on this. And I do have, for anybody watching this, you could, if you want to review, I have nice review sheets online. I go through it. The two types of hyperboloids, the three types of the two types of paraboloids, the three types of hyperboloids. I do examples. It's not that bad. But just if you don't understand what I mean by traces, this is what we're doing when we're fixing an x or a y. So for example, if we fix x and then move it, we're looking at those traces. Let's get rid of the shape for a second. We're just looking at cross sections. So from this direction, it's parabolas. Fun. Okay. From the y direction, it's also parabolas. Let's get rid of this. Let's draw that. So from two sides, it looks like a parabola. That's why we call it a paraboloid. That's where the name comes from. And then lastly, if we're going up, these are the visuals you get if you take Calculus 3 from me. I have a lot of these. You get an ellipse. So we call that an elliptical paraboloid. Here's a hyperboloid of one sheet. Notice a few things. What happens when we change this number is it changes the trace for z. Let me show you that trace. Here's z. So there's that circle in the middle. Currently, the radius of that circle is the square root of k. Okay, so if we make k smaller and smaller, I love this picture. It's like a lava lamp. Eventually, you get a 0 on this side, and you just get a very skinny circle, and then it's not possible to have a circle there. That's it. That's what's going on. Those are all just hyperboloids. Paraboloid of two sheets, and then this number becomes 0. It's a cone. Ah, lovely. I love that picture. And then, okay, so then I'll say one more thing before we go on. So when you go to do the exams, it's just we needed a few names before we move forward in this course. So let me show you that. Okay, so I found a few old exams that aren't mine. We're given this kind of messy thing. First it says, what's the trace when you put in a 1 here? Well, if you put in a 1 there, you're going to have an x squared plus z squared equals -2. This is something you encountered in the homework. Sometimes it's a little easier if you complete the square. 1/2 of that squared would be 1. So x squared minus 2x plus 1 minus 1. This is not actually necessary, but I'm just doing it real quick. Plus z squared equals -1. Draw the trace. Oh, this was supposed to be a 4. I was going to say, that didn't work out very nicely. So we add that over, we get a 2. That's a circle. A circle of radius square root of 2. I don't think I missed anything there. Right. So you have a circle centered at 1, z of radius square root of 2. Square root of 2 is a little bigger than 1, so I drew it incorrectly. But that's it. So now you've gotten one of the traces. But in terms of naming, it is, if we wanted a real formal process, we would always complete the square. Then you would have minus y squared plus 4y plus z squared. So it does have a little more to it. Half the middle. So we're going to y squared plus 4y plus 4 minus 4 plus z squared. Now you could do all of this by just doing the same cover-up idea. But if I had to graph this, I definitely would want to do some completing the square. I'm going to distribute. That's going to make that a plus 4 plus z squared is minus 2. So I get x minus 1 squared. And these little adjustments just shift it left or right. But the real takeaway from this is the following. All three things have a square. We could have seen that back here. All three things have a square. These extra y's and x's shift things, but the moment I see that, I go, okay, we're talking about a hyperboloid. All three things are squared. Going back up here. Just what type of hyperboloid is it? 1 sheet, 2 sheets, or a cone? And so you're trying to chase down the number on the other side. Or you're trying to replace, this is why they were trying to help you here, is they had you plug in this 1 to see, oh, we did get something there. But anyways, the fact that this is a positive means even when this thing is gone, you still get something. And so it's a hyperboloid of 1 sheet. So there was a little more trickiness to that one, but I hope you get the idea. The main place we use these things is to help us visualize a 3D curve. So if somebody gives me this is some curve in 3D. I don't know very much about it. I'd have to do a lot of work to analyze it. But sometimes we can eliminate the parameter and get a shape, and that helps us graph it. And the main thing I notice here is that there's a sine and cosine. This is more of a chapter 13 thing, but sine squared plus cosine squared is always 1. And if you see some equations where you see sines and cosines, think of this. Because what you can do is you can move this to the other side and say, this is the same as x over 2t, and this is the same as z over t. Why is that helpful? Well, let's see. This is going to be x squared plus 4t squared. This is going to be z squared, t squared, and that has to be 1. What can I do? I can multiply everything by t squared, and then I would have this. Now I still have this darn t, but can I get rid of it? Yes, I can. T squared is... So this is this idea of trying to manipulate it in a way that gets rid of your t. Now this and this are not the same. This is a surface. This is a curve on that surface. But this helps me visualize. Now what is that? 2 are squared, 1 is not. Let's play the trace game. If you cover up y, you're getting an ellipse. An ellipse because there's a plus between them, there's different numbers. If you cover up x, you're getting a parabola. If you cover up z, you're getting a parabola, an elliptical paraboloid. So this is an elliptical paraboloid. And what's nice is if you were then going to visualize that thing, and I'll give an example here. This is not the same one, but this is an example of something that's moving along a cylinder. That just helps me visualize. There's the curve. There's the thing we're studying. But knowing that the curve is always on the cylinder helps me. And it helps me if I'm trying to visualize it. It helps me if I'm trying to graph points moving. So I sometimes call that a surface of motion. But if you don't know any surfaces, you can't use that. And so that's how I think of the section 12.6, is giving us a few surfaces to work with. Okay, I hope that makes sense. That section should not scare us. Typically on an exam, there's just a small question about this, but I hope that gives you a little more background, and watch my other resources if you need.